Hello everyone, my name is Thomas Kim. Today is October 8th, 2024. It is 3:48 a.m. I asked ChatGPT like this. Now list metrics commonly used in mathematics and physics. Then ChatGPT lists commonly used metric in mathematics and physics. First, Euclidean metric. This formula must look familiar. Then, second, Minkowski metric, flat spacetime special relativity. This metric is commonly used in special relativity. Then, third, Riemann metric, curved space. This metric might look unfamiliar if you don't have experience in tensor. Then, fourth, Lorentzian metric, curved spacetime, general relativity. This metric may not look familiar with you if you do not have experience in general relativity. Fifth, spherical metric on sphere. This metric may look familiar or unfamiliar depending on your experience with vector calculus. Sixth, Schwarzschild metric, black hole spacetime. This metric might look very challenging, but you will capture this metric instantly. Seventh, Robertson-Walker metric, cosmology. This metric may look challenging. Poincare metric, hyperbolic space. This metric may look unfamiliar for most of us. Fubini-Study metric, complex projective space. This metric may not look familiar with you. 10th, Kerr metric, rotating black hole spacetime. This metric may look overwhelming. Summary of common metrics. So, Euclidean metric, Minkowski metric, Riemannian metric, Lorentz metric, Lorentzian metric, spherical metric, Schwarzschild metric, Robertson-Walker metric, Poincare metric, Fubini-Study metric, Kerr metric. These are commonly used metrics in mathematics and physics. If you follow my current session, all these overwhelming metrics or equations, you will catch up or pick up all these things intuitively. If you watch through my current session, you can pick up or catch up all these equations intuitively. You don't need to memorize any of these things. You can just know. I said you can just know. I asked ChatGPT like this. Explain Riemannian metric. Label mathematical expressions with numbers such that I can refer to them. To this,
the Riemann metric is a fundamental concept in differential geometry, which provides a way to measure distances and angles on curved surfaces or manifolds. It allows us to define notions like length, area, and curvature in a way that generalizes our intuitive understanding from Euclidean geometry. Definition: a Riemannian metric on a differentiable manifold, M, is a smooth assignment of a positive definite inner product on the tangent space at each point of the manifold. This is expressed mathematically as follows. 1. For each point, P and M, let TPM denote the tangent space at P. The Riemannian metric, G, can be written as GP TPM times TPM to Mar 1. The metric, GP, is required to satisfy the following properties. Symmetry, GPXY equals GPYX, for all XY in TPM. Positivity, GPXX0, for all non-zero X in TPM. Linearity, GP is linear in each argument. Riemannian metric in local coordinates. In local coordinates x1, x squared dots x squared around a point P, the Riemannian metric can be expressed in terms of the components Gij as G equals Gij dx squared O times dxj 2, where Gij are smooth functions on M that define the inner product of tangent vectors. The notation dx squared I O times dxj represents the tensor product of differential forms. Length of curves. The length of a smooth curve, gamma t, on the manifold from t equals a to t equals b can be defined using the Riemannian metric. L gamma equals inter a equal b, skirt g gamma t, dot gamma t dt. 3, where dot gamma t is the tangent vector to the curve at gamma t. Distance between points. The distance dpq between 2 points, p, q, and m, can be defined as the infimum of the lengths of all curves connecting p and q. dpq equals inf gamma elv gamma 4, curvature. The curvature of a Riemannian manifold can be characterized by the Riemann curvature tensor, R, which is derived from the Riemannian metric. The Riemann curvature tensor provides information about how the manifold deviates from being flat. It can be defined as Rx, y, z equals nabla x, nabla y, z, nabla y, nabla x, z, nabla x, y, z, where nabla is the Levi-Civita connection and x, y, z are tangent vector fields. The Riemann metric is crucial for understanding the geometry of curved spaces. It allows for the generalization of various geometric concepts such as lengths, angles, and curvature to more complex settings beyond flat Euclidean spaces. The definitions and expressions labeled above provide a foundational understanding of how distances and shapes are described in Riemannian geometry. If you have specific questions about any of these expressions or concepts, feel free to ask.
What do you call the operator in 2?
The operator in expression 2, g equals gij dxi o times dxj, is called the Riemannian metric tensor. Specifically, g, I, j are the components of the metric tensor, and the expression represents a 0-2 Strasbourg tensor, which is a bilinear form that takes two tangent vectors as input and returns a scalar, real number. The tensor product indicates that the metric tensor combines the differentials dx square I and dxj to form a tensor that can measure distances and angles on the manifold. In this context, the metric tensor provides a way to define the inner product between tangent vectors at a point on the manifold.
Tensor product. Is it inner product or exterior product in 2?
In expression 2, the term g equals gij dx square I o times dx square j involves the tensor product of differential forms. Specifically, the tensor product, O times, indicates that we are constructing a bilinear form, which is used to define the Riemannian metric. This is not the same as an inner product or an exterior product. Clarification of terms. 1. Inner product. The Riemannian metric tensor G defines an inner product on the tangent space at each point. If x, y are tangent vectors, then the inner product is given by G, x, y. 2. Exterior product. The exterior product is used in the context of differential forms to construct higher degree forms, e.g. taking two 1 forms to create a 2 form. It is denoted with the wedge product, wedge, e.g. alpha wedge beta for 2 forms, alpha and beta. This is not applicable in the expression for the metric tensor. Conclusion. So in expression 2, the tensor product is utilized to define the Riemannian metric in terms of the components gij. It constructs a 0-2 tensor that can be used to compute the inner product of tangent vectors, rather than representing an inner or exterior product directly.
What is the name of the tensor product operator used in 2? How can I address it when I communicate with you?
The tensor product operator used in expression 2 is commonly referred to as the tensor product symbol, denoted by OTIMs. When communicating with me, you can simply refer to it as the tensor product operator, or just tensor product. If you want to be more specific, you can mention the tensor product operator in expression 2, Taro, and I'll understand that you are referring to O times in that context. To expand expression 2 in matrix format, we need to consider how the Riemannian metric tensor G can be represented in terms of its components and the basis of the tangent space. Riemannian metric in matrix format. Let n be the dimension of the manifold M. The components Gij of the Riemannian metric tensor can be organized into an n times n matrix G, G matrix, G11 and G12, and C dots in G1n, G21 and G22 and dots and G2n, dots of V dots, Gn1 and Gn2 and dots and Gnn, B matrix. This matrix G represents the Riemannian metric tensor in a chosen coordinate basis, Each entry, Gij, corresponds to the inner product of the basis tangent vectors frac partial x squared I and frac partial x squared j. G left frac partial x squared I partial x squared a right equals Gij with tag 1. Expression of the metric, the Riemannian metric. The Riemannian metric can then be expressed in terms of the matrix G and the vector of differentials, math bf dx. G equals dfs, where bx is the column vector of differentials. Also dx begin B matrix dx squad x v dots, full expression. Putting this all together, the Riemannian metric can be written in matrix form as G equals begin B matrix, dx1 and dx squared and c dots and dx squared B matrix, G11 and G12 and c dots and G1n, G21 and G22n, v dots and v dots and g dots, Gn1 and Gn2 and c dots and Gnn, dx1, dx2, dxn. This expression captures the essence of the Riemannian metric tensor in a matrix format, showing how it relates to the differentials of the coordinates on the manifold.
Please do not forget labeling each math expressions in your response. Otherwise, I cannot communicate with you further. Please, I beg you. This is the same. G in 5 is called Riemann metric and is commonly denoted as G, Gij, dxi, tensor product, dxj.
Yes, that's correct. In expression 5, G represents the Riemannian metric, and it is commonly denoted as G equals Gij, dx squared I, O times dxj tag 6. Explanation. Here, Gij are the components of the metric tensor, which capture how distances and angles are measured in the manifold. The notation dx squared I O times dx squared j indicates the tensor product of the differential forms, forming a bilinear map that defines the inner product of tangent vectors at each point on the manifold. This expression succinctly encapsulates the relationship between the Riemannian metric and the differential forms in the context of the manifold's geometry. You can refer to expression 6 in our discussions as needed.
Now, scroll down. G in 5 is called Riemannian metric and is commonly noted as a G equals Gij, dxi tensor product, dxj. How can I associate Gij, dxi tensor product, dxj with dx, t, g dx? Here, equation 5. This is equation 5, or this is equation 5.
The relationship between the two expressions for the Riemannian metric, G equals Gij dx thir I O times dxj, expression 6, and G equals math bf dx with tg math bx, expression 3, can be understood as follows. How to understanding the relationship. 1. Matrix representation. In the expression G equals Gij x sky items dxj, the Gij components represent the entries of the metric tensor matrix G in the context of a chosen coordinate basis. Here, the autumn symbol indicates that we are taking the tensor product of the differentials dx squared I and dxj. 2. Inner product form. The expression G equals math bf dx tg math bf dx represents the metric as a quadratic form, which computes the inner product of the differential vector math dx with respect to the metric tensor G. Here, math bf dx is the column vector of differentials given by math bf dx equals begin B matrix dx1, dx, and B matrix. Connecting the two expressions. To see how these two expressions are associated, consider the following. Expanding G equals math bx tg math bf dx. Chan, when you compute the expression math bf tg math dx, you are effectively summing over the products of differentials weighted by the components of the metric tensor. G equals sum equals 1 squared n, sum j equals 1 squared and Gij dx squared j, 7. This shows that G can be expressed as a sum of the products of the differentials dx squared I and dx the j multiplied by the corresponding metric components, Gij. From tensor product to quadratic form, the expression G equals Gij dx squared I indicates a bilinear form, while G equals math bf tgg math b dx represents the same bilinear form in a compact quadratic form using matrix notation. Thus, the two expressions are essentially different representations of the same geometric quantity, the Riemannian metric. Summary. In summary, the expression g equals gij dx squared I, O times dx squared j, describes the Riemannian metric as a tensor product of differentials weighted by the metric components, while g equals mathbf dx squared t g mathbf dx compactly represents the same metric as a quadratic form involving the metric tensor matrix G. You can refer to any of these expressions by their respective numbers if you have further questions.
I'm totally at a loss because you did not use unique numbers for each math expression. I cannot refer to different equations from your two different responses. What should I do? Why should I repeat the same thing every each session, every each question? I have to ask you the same thing again and again, endlessly.
I sincerely apologize for the confusion and frustration caused by the lack of unique numbering in my responses. Thank you for your patience. Let's clarify the relationship between the Riemannian metric expressed in both forms with unique numbering for each mathematical expression. Share Riemannian metric expressions 1. Tensor product form. The Riemannian metric can be expressed as g equals gij dx items dx squared j, where gij are the components of the metric tensor and dx squared I are the differentials. 2. Quadratic form. The Riemannian metric can also be expressed in matrix notation as g equals math bf dx squared tg math bf's d tag 2, where g is the matrix representation of the metric tensor and math dx is the vector of differentials. Math bf dx equals begin B matrix, dx1, dx2 v dots, dx1 and B matrix. Connecting the two expressions. To see how these two expressions are associated, we can expand the quadratic form. Expanding the quadratic form. When you compute the expression from 2, you have g equals math dxtg, math bf dx equals sum I equals 1 squared n, sum j equals 1 squared n, gij, dx squared I, dx squared a tag 4. This shows that g can be expressed as a sum of the products of the differentials, dx squared I and dx squared j, weighted by the metric components, gij. Summary of the relationship. Expression 1 describes the Riemannian metric using the tensor product of differentials. Expression 2 represents the Riemannian metric as a quadratic form involving the matrix G. Expression 4 connects the two forms by showing that they yield the same result through the summation of the inner products of the differentials, weighted by the components of the metric tensor.
Equation 4 ends up dr.
Yes, that's correct. The expression 4 can be interpreted in the context of a Riemannian metric for a curve parameterized by t in terms of a differential form. Let's break it down step by step. Expression expansion. From expression 4, g equals sum I equals 1n, sum j equals 1n, gij, dxi, dx tag 4. This summation represents the Riemannian metric in terms of its components, gij and differentials dxi and dx squared j. 1. Relating to differential, dr. If we consider a curve parameterized by t, where rt is the position vector, we can express the differentials dxy in terms of dr. One differential of the position vector, dr equals begin B matrix, frac dx1 dt, frac dx squared dt, v dots, dx1 dt and B matrix, dt equals dot r d tag 5, where dot r is the derivative of the position vector with respect to t. 2. Quadratic form in terms of dr sen, substituting dr into the metric expression gives g equals sum equals 1 quad and sum j squared and gij dot rri dot rj, where rri are the components of the tangent vector. Final expression. In the limit as dt to 0, we can express the infinitesimal distance along the curve as ds squared equals g equals gij dr clear I dr squared to 7. This indicates that the Riemannian metric, g, measures the squared infinitesimal distance, ds squared, along the curve, represented by the dot product, dr, c dot dr, in terms of the tangent vector components. Conclusion. So you are correct in that the expression can be interpreted as relating to dr dot dr, which captures the idea of measuring distances along a curve in a Riemannian manifold. If you need further clarification or have additional questions, feel free to ask.
Why we have tensor product form and quadratic form and dr dot dr form.
The tensor product form, quadratic form, and the expression involving d.docker are different ways to represent the same underlying concept of the Riemannian metric. Each form serves a specific purpose and provides different insights into the geometry of the manifold. Here's a breakdown of why each representation is used. 1. Tensor product form expression, G equals Gij, dx squared O times dx squared j. Purpose. The tensor product form explicitly shows how the Riemannian metric is constructed from its components, Gij, and the differentials, dx squared I. It highlights the bilinear nature of the metric, emphasizing that the metric tensor takes two tangent vectors as inputs and returns a scalar value, the inner product. This form is essential for understanding how the metric can vary across different points in the manifold. And number 2, quadratic form expression G equals mathbf dx squared t dx, tag 2. Purpose. The quadratic form compactly represents the Riemannian metric using matrix notation, making it easier to compute and manipulate, especially in higher dimensions. It allows for a straightforward calculation of the metric by simply using linear algebra techniques, which is useful for numerical applications or when dealing with coordinates in a more abstract way. This form is particularly helpful in calculus and differential geometry when computing lengths, areas, and volumes. Now 3. dr.dr form expression. ds squared equals g equals gij, dr through I, dr. Purpose. The dr.dr form emphasizes the geometric interpretation of the metric as measuring distances on the manifold. It expresses the infinitesimal distance, ds, along a curve in the manifold in terms of the differential dr, capturing the idea that the Riemannian metric gives rise to a notion of length. This representation is particularly intuitive and aligns closely with the physical interpretation of distances, making it suitable for applications in physics and engineering. Summary. Each representation serves a different role in understanding and utilizing the Riemannian metric. Tensor product form 1. Focuses on the mathematical construction of the metric and its properties. Quadratic form 2 provides a compact and computationally efficient way to work with the metric. dr form 3 highlights the geometric and physical interpretation of distance on the manifold. Together, these forms enrich our understanding of Riemannian geometry and its applications across various fields. If you have more specific questions about any of these forms or their applications, feel free to ask.
All three forms end up with a summation.
Yes, all three forms ultimately involve summation, reflecting the underlying structure of the Riemannian metric. Here's how each form concludes with a summation. Hag 1. Tensor product form. Expression. G equals Gij, dx squared I O times dx squared j, tag 1. Summation. This expression implicitly includes a summation over the indices I and j due to the Einstein summation convention, which states that repeated indices are summed. Thus, it can be rewritten as G equals sum I equals 1 equals 1 squared n Gij dxi dx squared tag 2. Quadratic form expression. G equals math bf dx tg math 3. Summation. When expanding this expression, we have G equals sum I equals 1 then Gij dxk. Here, the matrix multiplication involves summing the products of the components of G with the differentials dxy and squared j. Nar 3. dr.dr form expression. ds squared G equals Gij dr Summation. Similar to the previous forms, this expression also implies a summation over the indices. G equals sum I equals 1n, sum j equals 1n, g cry j, where dri represents the differentials of the coordinates along the curve. Hash summary. In all three forms, the summation reflects the bilinear nature of the Riemannian metric. Each form involves summing over the contributions from all pairs of components of the metric tensor and the differentials, highlighting how the Riemannian metric measures distances and angles in the manifold. If you have any more questions or need further clarification, feel free to ask.
For computational aspect, 3 is straightforward.
You're absolutely right. From a computational perspective, expression 3, the quadratic form, is indeed straightforward and particularly advantageous for various reasons. Advantages of the quadratic form 3. 1. Matrix operations. The quadratic form, G equals BF dx tg math BF dx, leverages matrix multiplication, which is well supported in many programming languages and numerical libraries. This allows for efficient computation, especially in higher dimensions. 2. Compact representation. It provides a compact representation of the metric, reducing the complexity of writing out all components individually. This is especially beneficial when dealing with large data sets or high-dimensional spaces. 3. Ease of implementation. In practical applications, implementing the quadratic form allows for straightforward coding. One can easily define the metric tensor, G, as a matrix and compute distances or lengths without needing to manage nested summations explicitly. 4. Numerical stability. Matrix operations can take advantage of optimized algorithms in numerical libraries, leading to improved performance and numerical stability compared to manually implementing summation loops. 5. Integration with algorithms. Many algorithms in numerical linear algebra, optimization, and machine learning utilize matrix representations, making the quadratic form naturally compatible with these methods. Example: in practice, if you have a Riemannian metric tensor, G, and want to compute the length of a curve defined by the differentials, mathbx, you would simply perform Python import numpy as np. Example of a metric tensor G and differentials dxg equals np.array g12, g21, g2. Metric tensor dx equals np.array.
dr can be more straightforward.
Absolutely. The expression dr.dr is indeed a very intuitive and straightforward representation of the Riemannian metric, particularly in the context of measuring distances. Here's why it is considered more direct. Advantages of dr.dr. 1. Geometric intuition. The expression ds2 equals dr directly relates to the concept of distance in a geometric context. It provides a clear interpretation of how the metric measures the length of infinitesimal displacements along a curve in the manifold. 2. Simplicity. This form is simpler and more natural to visualize, especially when considering paths or curves in the manifold. It emphasizes the idea that you are computing the squared length of an infinitesimal vector, dr. 3. Immediate application. In physical contexts, particularly in general relativity and differential geometry, ds2 equals gij, dr j is often used to calculate lengths, areas, and volumes directly without intermediate steps. 4. Directness in calculations. When dealing with curves or surfaces, writing ds2 equals dr allows for immediate computation of distances or areas, reducing the need for summation or more complex tensorial notation. Example of use. If you have a parameterized curve, rt, then dr equals frac dt. The squared differential distance can be expressed as ds squared equals gij, dr squared I, dr j. This leads directly to computations involving the lengths of paths or surfaces, making it a straightforward and powerful approach. In summary, the dr form is favored for its simplicity and direct relationship to geometric concepts, making it very effective for both theoretical exploration and practical applications in differential geometry. If you have further thoughts or specific areas you'd like to delve into, feel free to share.
So, all these forms are created or defined by Riemann.
Yes, all these forms of the Riemannian metric are derived from the foundational work of Bernhard Riemann, who made significant contributions to differential geometry and the study of curved spaces. Here's a brief overview of Riemann's contributions and how they relate to these forms. Riemann's contributions. 1. Riemannian geometry. Riemann introduced the concept of a Riemannian manifold, which is a smooth manifold equipped with a Riemannian metric. This metric allows for the measurement of distances and angles on the manifold, generalizing notions from Euclidean geometry to curved spaces. 2. Metric tensor. Riemann's work established the metric tensor as a fundamental object that captures the intrinsic geometric properties of a manifold. The metric tensor, gij, is a bilinear form that can be represented in various ways, including the tensor product and quadratic forms. 3. Riemannian metric. The Riemannian metric itself is defined by g equals gij dx squared I o times dx squared j, where the components gij encapsulate how distances are computed on the manifold. This definition is critical for expressing geometric concepts in the context of curved spaces. Forms derived from Riemann's work. 1. Tensor product form. This form expresses the metric in terms of its components and differentials, emphasizing the bilinear nature of the metric tensor. 2. Quadratic form. The quadratic form represents the metric compactly using matrix notation, making calculations easier and more efficient, especially in higher dimensions. 3. Infinitesimal distance, dr. This form captures the idea of measuring distances directly, providing a geometric interpretation of the Riemannian metric. Summary. In essence, these forms are all manifestations of Riemann's foundational ideas in geometry, allowing us to understand and compute distances, angles, and other geometric properties in a rigorous way. His work laid the groundwork for much of modern differential geometry, and the various representations of the Riemannian metric reflect the versatility and depth of his contributions.
Please do not forget labeling math expressions. If you forget, my next question is hard to form. It is my broken English. It is hard to form my next question.
Thank you for your patience. Here's the information with properly labeled mathematical expressions for easy reference. Riemann's contributions. 1. Riemannian geometry. Riemann introduced the concept of a Riemannian manifold, which is a smooth manifold equipped with a Riemannian metric. This metric allows for the measurement of distances and angles on the manifold, generalizing notions from Euclidean geometry to curved spaces. 2. Metric tensor. Riemann's work established the metric tensor as a fundamental object that captures the intrinsic geometric properties of a manifold. The metric tensor, Gij, is a bilinear form defined as G equals Gij d times dxj tag 1, where Gij are the components of the metric tensor, and dxy are the differentials. 3. Riemannian metric. The Riemannian metric can also be expressed in a compact quadratic form as G equals math bx squared tg math dx tag 2, where G is the matrix representation of the metric tensor and math dx is the vector of differentials. Math bf dx equals begin B matrix x1 dx squared v dots dx squared n and B matrix. 4. Infinitesimal distance. The infinitesimal distance can be expressed as ds2 equals gij dr squared I dr tag 4, where dr squared I represents the differentials along a curve in the manifold. Hash summary. All these forms are derived from Riemann's foundational work in differential geometry, allowing us to compute distances, angles, and other geometric properties in a rigorous manner. If you have further questions or need clarification on any specific expression, feel free to refer to them by their numbers.
In 1, terms are summed up. I and j runs from 1 to n, where n is dimension of the vector. 2, dxi and dxj are differentials of a vector. For example, r x1, x2, xn. 3, why they use tensor product symbol.
You're correct with your first two statements. And now let's address your third question about the use of the tensor product symbol, O times, in expression 1. Why use the tensor product symbol? The use of the tensor product O times in expression 1, G equals Gij, dxy O times dxj, tan, has specific reasons related to the structure and properties of the Riemannian metric. Here's why the tensor product is used. 1. Tensorial nature of the metric. The Riemannian metric is a 002 tensor, which means it takes two tangent vectors and outputs a scalar. The tensor product dx squared I O times dxj represents this bilinear nature. The tensor product between dxy and dx squared j means that this metric is bilinear. It takes two inputs, tangent vectors at a point, and computes the inner product between them. In other words, for two vectors, x and y, the metric gives a scalar via gxy gij yjeg 2. This computation involves combining components of the tangent vectors using the metric tensors, a gij. 2. Bilinear mapping. The tensor product O times expresses a bilinear mapping, which is crucial for defining the inner product between two tangent vectors. In simple terms, the tensor product describes how differentials dx squared I and dx squared j interact in all possible combinations to define distances, angles, and areas in the manifold. The metric tensor G weights these combinations. 3. Tensor product versus dot product. A dot product applies to vectors in Euclidean space and produces a scalar directly. However, on a Riemannian manifold, the inner product of two tangent vectors can vary from point to point depending on the geometry. The tensor product allows the metric tensor Gij to describe the inner product in a flexible and generalized way, accommodating the manifold's curvature and non-Euclidean structure. Local definition of geometry. The metric tensor defines geometry at every point of the manifold. The expression dxi o times dxj ensures that the geometry, distances, and angles is described consistently across the entire manifold by combining the differentials in a structured way. The use of the tensor product in 1 reflects the bilinear and tensorial nature of the Riemannian metric. It allows the metric to generalize the concept of an inner product to curved spaces, enabling the measurement of lengths, angles, and areas in a more flexible, geometrically consistent way. If you need further clarification on this or any other topic, feel free to ask.
How do you express R, x1, x2, x3 if we define R partial R over partial x1 dx1 plus partial R partial x2 plus partial R partial x3? In such case, how do you express G in tensor product form? Here, I missed dx2, here dx3. I missed dx2 and dx3 here.
To express math BFR x1, x2, x3, and the Riemannian metric G in the tensor product form based on the definition of dr, let's break this down step by step. 1. Expressing math R x1, x2, x3. Let math R x1, x2, x3 be a position vector in a three-dimensional space, such that the coordinates x1, x2, x3 parameterize the space. Then, the differential dr of the vector math BFR x1, x2, x3 can be expressed as dr equals frac partial math R partial x1 dx1 plus frac R partial x2 dx2 plus frac partial x3 dx3 tag 1. This expression describes how the vector math R changes with respect to each of the coordinates x1, x2, x3. Sharp 2. Tensor product form for the Riemannian metric. Now, if we want to express the Riemannian metric G in tensor product form, we need to think about how the metric acts on the differentials dx1, dx2, dx3. The Riemannian metric is a 0-2 tensor, so it takes two differentials and produces a scalar that measures the infinitesimal distance. The general form of the Riemannian metric in tensor product form is G equals Gij dx squared I o times dxj tag 2. For three-dimensional space, G will involve the summation of products between differentials dx1, dx2, dx3, and the components of the metric tensor Gij. Har 3. Applying to dr, if dr is the differential of math BF R, we substitute it into the Riemannian metric expression. Since the metric tensor Gij gives the inner product of differentials, the metric in tensor product form becomes G equals left frac math R partial x1 c dot frac partial math bar partial x1 right dx1 o times dx1 plus left frac partial math BF R partial x1 frac partial math R partial x2 right dx1 o times dx plus q dot x3 dot frac math 3 partial x3 right dx3 o times 3 3. In this form, each term Gij equals frac partial math R frac partial xj represents the components of the metric tensor, and the tensor product dxi o times dxj captures the bilinear nature of the Riemannian metric. 4. Summation of terms. The full expression for the Riemannian metric G can be written as G equals sum E equals 1 3 sum split of 3 zlek frac partial math BR partial xi dot frac partial math BFJ right dxi o times dxj tag 4. Conclusion. To summarize, math BFR x1, x2, x3 is the position vector. The differential dr is expressed as in 1. The metric tensor G in tensor product form is given by 2 and expanded in terms of the derivatives of math FR as shown in 3 and 4. This formulation allows us to compute the Riemannian metric using the components of the position vector math R and the tensor product dx squared I O times dxj represents the bilinear nature of the metric.
Are you sure of 4?
You're right to question 4. Upon reviewing it, I see that it's not entirely correct. The relationship between Dialog and the Riemannian metric should be clarified more carefully. Let's correct it. Corrected explanation. Given the vector mathbef r x1, x2, x3, the differential of mathbef r is dr equal frac partial math s1 dx1 plus frac partial math r partial x2 dx2 plus frac partial x3 dx3 1. Here dr is the differential of the position vector in three-dimensional space, where each term represents how the vector bfr changes with respect to each coordinate. Number 1, Riemannian metric. The Riemannian metric, g, is used to compute the infinitesimal squared distance, ds squared, and it's typically written as ds squared equals gij dx squared I dx squared 2. Here, gij are the components of the metric tensor, and dx squared I dxj are the differentials of the coordinates. 2. Relating g and dr. When we use the expression for dr, it represents how the vector math bfr x1, x2, x3 changes in response to changes in the coordinates x1, x2, x3. The Riemannian metric computes the squared length of dr, so ds toward is computed as ds2 equals dr tag 3. This is essentially a dot product of the differential vector, dr, with itself, and it can be expanded in terms of the components of the position vector, math r. Harmachar 3. Correct tensor product form. In the tensor product form, the Riemannian metric, g, can be written in terms of the components gij, which depend on the derivatives of the position vector, math r. G equals sum I equals 1 quad 3, sum did left partial math bfr partial xi, stat frac partial math br partial xj, dx I times dx squared j, tag 4. This form is correct because the components of the metric tensor gij are given by the inner product of the partial derivatives of the position vector math r. Gij equals frac partial math r partial xi, cdoc partial math r partial xj, tag 5. So, the metric tensor gij describes how the position vector changes in response to the different coordinates, and the tensor product dx squared I O times dxj represents the differentials of the coordinates. Conclusion. In summary, the metric tensor components gij are given by the inner product of the partial derivatives of the position vector as shown in 5. The Riemannian metric in tensor product form is correctly written in 4. The dot product form ds2 equals dr c dot dr simplifies the computation of the infinitesimal squared distance as shown in 3. If this explanation is now clearer, feel free to refer to specific expressions for further questions.
In 4, the dot represent multiplication or dot product.
Yes, in practice, the tensor product dxy dxj often gets simplified to just dx squared I dxj, especially when the context makes it clear that you are dealing with a bilinear form like the Riemannian metric. Here's why. 1. Tensor product times in expression 4, g equals sum I equals 1 hat 3, sum j equals 1 3, left frac partial math bar partial xi, partial xj, right dx squared I times dxj, tag 4. The tensor product O times emphasizes the bilinearity of the metric, showing that gij acts on two differentials, dxi and dxj, in a structured way. However, because we are dealing with a 0-2 tensor, the metric, we can write it more compactly as dx squared I dxj, dropping the explicit times when the meaning is clear from context. 2. Simplification to dxy dx squared j. In most cases, particularly when calculating distances or lengths, it's common to omit the tensor product symbol and write g equals sum equals 1 squared 3, sum j equals 1 3, gij, dx squared dxj tive. Here, dx squared dxj represents the product of the differentials, and the meaning is understood to be bilinear, i.e. acting on two differentials in a way consistent with the metric. Conclusions, dx squared times dxj often simplifies to dx squared dxj in expression 5 because the bilinear nature of the Riemannian metric is implied. The tensor product can be dropped for simplicity, and it is commonly written this way in practice. If you need further clarification or have additional questions, feel free to ask.
The tensor product emphasizes bilinearity of the metric showing that Gij acts on two differentials dxi and dxj in a structured way. What do you mean by bilinearity in the bilinearity of the metric?
When I refer to the bilinearity of the metric, I mean that the Riemannian metric, G, behaves as a bilinear map on the tangent space. In more detail, a function or operation is bilinear if it is linear in each of its two arguments separately. Let's break this down in the context of the Riemannian metric. Hash number 1. Bilinearity of the metric. The Riemannian metric G is a 0-2 tensor, meaning it takes two input vectors, tangent vectors, at a point on the manifold and produces a scalar. The metric is bilinear because it satisfies the following properties. Linear in the first argument. If x and y are tangent vectors, then for any scalars a and b and tangent vectors x1 and x2, g of ax1 plus bx2 y equals ag of x1y plus bg x2y tag 1. This shows that G is linear in its first argument. Linear in the second argument, similarly for any scalars a and b and tangent vectors y1 and y2. G of x ay1 plus by2 equals ag of xy1 plus bg x2. This shows that G is also linear in its second argument. Number 2. Tensor product and bilinearity. The expression for the metric tensor using the tensor product dxi of dxj, as in G equals gij dx square I items dx square tag 3. Emphasizes that the metric acts on two differential forms, dx square I and dxj, and combines them bilinearly. This means that G computes quantities by combining the products of differentials dx squared I and dx squared j in a linear way with respect to both variables. The tensor product expresses this bilinearity clearly, indicating that the metric takes two inputs, differentials or vectors, and produces a scalar by applying the linearity rules in both arguments. 3. Example of bilinearity. Let's look at an example. If G is the Riemannian metric, and x equals x square I partial x thide, and y equals y squared j frac partial x j are two tangent vectors, then the metric gives G of xy equals gij x square I yj tag 4. This expression is bilinear because the result is linear in x square I, the components of x. The result is also linear in yj, the components of y. Hasher 4. Bilinearity in differential geometry. In differential geometry, bilinearity is crucial because it allows the metric to combine tangent vectors at a point smoothly and linearly. It ensures that properties like length, angle, and distance can be computed consistently as the vectors change. Summary. The bilinearity of the Riemannian metric means that the metric is linear in both of its arguments, two tangent vectors or differentials. This property allows the metric to compute inner products, lengths, and angles in a structured, predictable way. The tensor product in dxi dxj explicitly shows that the metric operates on two inputs, emphasizing this bilinear nature. I hope this clears up the meaning of bilinearity. Let me know if you have further questions.
There can be G equals Gij dxi tensor product dxj tensor product dxk too?
Yes, there can be an expression of the form G equals Gij dx square I otims dxj otims dx square k, but it would not represent a Riemannian metric. Instead, this type of expression involves a 0-3 tensor, a third-order covariant tensor, which has a different geometric meaning compared to the Riemannian metric. Key differences and explanation. 1. Riemannian metric. The Riemannian metric is a 0-2 tensor, which means it takes two tangent vectors as inputs and produces a scalar. The metric tensor Gij's in this case describes distances, angles, and lengths, and is represented as G equals Gij times dx squared j, tag 1. This bilinear form reflects how the metric maps pairs of differentials or tangent vectors to a scalar. 2. Third-order tensor, Gij. A third-order tensor is a 0-3 tensor. It takes three tangent vectors or differentials and produces a scalar. G equals Gij, dxi o times dx square o times dx square tag 2. This is a trilinear map, meaning it is linear in all three arguments. Such a tensor would not represent a metric, which is bilinear, but instead could describe more complex interactions involving three vectors. For example, it could describe torsion in a geometric setting. In the context of physics, it might represent some other physical quantity, like certain kinds of field interactions, but it wouldn't describe distances or angles. 3. Geometric meaning. 0-2 tensor, Riemannian metric, measures lengths and angles via the bilinear form. 0-3 tensor, like GK, would measure something more complex, typically related to the interaction of three directions in space. For example, it could describe torsion or higher-order curvatures in differential geometry, but it is not used to describe basic geometric concepts like distance. 4. Examples of higher-order tensors. Torsion tensor. In differential geometry, the torsion tensor, Tijk, is a 1-2 tensor that can describe twisting in a space. Curvature tensor, the Riemann curvature tensor, Rh, is a 1-3 tensor that measures the curvature of space. This shows that tensors with more than two indices, like your example with 3 indices, describe more intricate geometric or physical properties. Summary: G equals Gij, dx by O times dx squared j, O times dx squared k represents a 0-3 tensor, which is a trilinear map. It would take 3 differentials or vectors as input and produce a scalar, but it wouldn't be a Riemannian metric. The Riemannian metric is always a 0-2 tensor and is bilinear. Higher-order tensors, like a STA003 tensor, could represent other geometric or physical properties, but they don't serve the purpose of defining distances and angles. If you have any further questions on this or related topics, feel free to ask.
0-2 tensor means it takes 2 vectors and return a scalar or zero-rank tensor. 1-2 tensor means it takes 2 vectors and returns a vector or one-rank tensor. 1-3 tensor means it takes 3 vectors and return a vector or one-rank tensor.
Yes, you're on the right track. Let me clarify each case and explain the notation for tensors and how they act. Tensor notation and rank. Shernzu, tensor means the tensor takes 2 vectors or covectors as inputs and returns a scalar, a rank 0 tensor. 1-2 tensor means the tensor takes 2 vectors as inputs and returns a vector, a rank -1 tensor. 1-3 tensor means the tensor takes 3 vectors as inputs and returns a vector, a rank 1 tensor. Now let's look at each of these in more detail. 1. 0-2 tensor takes 2 vectors, returns a scalar A. A02 tensor is a bilinear map that takes 2 tangent vectors x and y and returns a scalar, typically representing an inner product or a geometric property like distance or angle. Example: the Riemannian metric, G, is a 0-2 tensor. Action: gxy equals gij xy squared tag 1. Here, gxy is a scalar which is computed by the metric tensor using the components of the vectors x and y. Rank: since it returns a scalar, this is a rank 0 tensor. Nap to 1-2 tensor takes 2 vectors, returns a vector A. 1-2 tensor is a multilinear map that takes 2 tangent vectors and returns a vector, rank -1 tensor. This type of tensor is commonly found in differential geometry in objects like the Christoffel symbols. Example: the connection nebula is a 1-2 tensor, specifically a connection in a manifold. The torsion tensor is also a 1-2 tensor. Action: Txy equals Tijk xjyk frac partial at tag 2. Here, Txy returns a vector which can be thought of as a direction in the tangent space. The components T⁻ijk represent how the vectors x and y combine to produce the resulting vector. Rank: this is a rank 1 tensor because it returns a vector. 3. 1-1-3 tensor takes 3 vectors, returns a vector. A 1-3 tensor takes 3 vectors as input and returns a vector, rank 1 tensor. This is a higher order tensor, typically used to describe more complex geometric structures, like curvature. Example: the Riemann curvature tensor R is a 1-3 tensor. It takes 3 tangent vectors as input and returns a vector. Action: Rxyz equals Rijkl xjyk zql frac partial xy. Here, the Riemann curvature tensor Rxyz returns a vector that depends on how the input vectors x, y, and z interact, which is related to the curvature of the manifold. Rank: this is a rank 1 tensor because it returns a vector. Summary of tensor notation. PQ tensor, a tensor that takes q vectors as input and returns a p rank tensor. which could be a vector, scalar, or higher rank tensor. 0, 2, tensor, takes two vectors and returns a scalar, e.g. Riemannian metric. 1 mol 2, tensor, takes two vectors and returns a vector, e.g. connection or torsion. 1, 3, tensor, takes three vectors and returns a vector, e.g. Riemann curvature tensor. Each of these tensors has a different function depending on the number of vectors it acts on and what it returns, but the notation PQ tells you how many vectors it takes and what rank tensor it outputs. If you have any additional questions or would like further clarification, feel free to ask.
So, basically, tensor analysis or tensor calculus is the ultimate or highest level of tools to describe geometry in generic form.
Yes, tensor analysis, or tensor calculus, is indeed one of the most powerful and general tools for describing geometry in a rigorous and generic form, especially in curved spaces. It serves as the foundation for many advanced theories in both mathematics and physics, including differential geometry, general relativity, and various fields of engineering and science. Here's why tensor analysis is often considered the ultimate tool for describing geometry. 1. Generality and flexibility. Tensors are multilinear objects that can describe relationships between vectors, covectors, and higher-order objects in a very general way. They can be used to describe not just Euclidean spaces, but also curved manifolds like surfaces or higher dimensional spaces with arbitrary geometries. This is crucial for generalizing the concepts of distance, angle, and curvature from flat space to any manifold. Coordinate independence. One of the key advantages of tensors is their coordinate-free nature. Tensors do not depend on a specific coordinate system, making them the perfect tool to describe physical laws and geometrical structures that remain valid regardless of the choice of coordinates. For example, the Riemannian metric tensor allows us to measure distances and angles on any curved manifold in a way that doesn't depend on the particular coordinate system chosen to describe the manifold. Describing curved spaces. In differential geometry, which deals with curved spaces, manifolds, tensors provide the language to describe how these spaces are curved and how they behave locally and globally. For instance, the Riemann curvature tensor tells us how a manifold curves and how the curvature affects the geometry of the space. The metric tensor gives us a way to define the length of vectors, angles between vectors, and the shortest paths, geodesics, on the manifold. Number 4, physical applications, general relativity. Einstein's general theory of relativity is fundamentally written in the language of tensor calculus. The famous Einstein field equations are tensor equations that describe how matter and energy curve spacetime, and how this curvature affects the motion of objects. The stress-energy tensor describes the distribution of energy and momentum in spacetime, while the Einstein tensor describes the curvature of spacetime due to the presence of matter and energy. 5. Unified framework for multiple quantities. Scalars, vectors, and matrices are all special cases of tensors. A scalar is a 0, 0 tensor. A vector is a 1, 0 tensor. A matrix or bilinear form is a 0 to 2 tensor or 2 to 0 tensor. Tensors provide a unified framework to deal with all these different types of quantities in a consistent way. This is especially useful when transitioning between different forms of quantities in physical or geometric settings. Hacker 6. Describing multilinear relationships. In tensor calculus, you deal with multilinear maps, which generalize linear functions. This means that tensors can describe more complex relationships between geometric objects, like vectors, covectors, or differentials. For example, higher-order tensors, such as the Riemann curvature tensor or the Christoffel symbols, are used to describe the way a space curves or how paths bend in curved space, respectively. Number 7. Expressing differential equations. Many important differential equations in physics and engineering are naturally written in the form of tensor equations, because they describe how quantities change over space and time in a way that is independent of the coordinate system. Tensor calculus gives a powerful framework to deal with these equations, such as Navier-Stokes equations in fluid dynamics, which can be tensor equations. Maxwell's equations in electromagnetism, which can be expressed in tensor form. Einstein's field equations in general relativity. Summary. In summary, tensor analysis, or tensor calculus, is indeed one of the highest level tools for describing geometry and physical laws in a generic form. Its key strengths are generality, applicable to any dimension and type of space, curved or flat. Coordinate independence, describes geometric and physical laws in a form that doesn't depend on coordinates. Power, capable of describing complex relationships like curvature, torsion, and physical interactions in a unified framework. If you are working in any field that involves complex geometry, especially in curved spaces or multidimensional systems, like general relativity, continuum mechanics, or differential geometry, tensor analysis is the essential tool for understanding and expressing the underlying mathematics. Let me know if you'd like to dive deeper into any specific aspect.
In 2 and 3, what's partial xi mean?
In expressions 2 and 3, frac partial x squared I represents the partial derivative with respect to the coordinate x squared I. Specifically, 1. Partial derivative frac partial x squared I. This partial x squared I refers to the operation of taking the partial derivative of a function with respect to the coordinate x squared I. It measures how a function, or a component of a vector field, changes as x squared I varies, while keeping the other coordinates constant. In a local coordinate system, x squared dots x squared n, frac partial xi is one of the fate basis vectors of the tangent space at a point on the manifold. It indicates the direction in which the function is changing as x squared I changes. For example, if f of x1 x squared dots x squared n is a scalar function, then frac partial x squared I represents how f changes with respect to the coordinate x squared I, while all other coordinates are held fixed. Number 2. In the context of tensors, expressions 2 and 3, in the context of tensors, frac partial x squared I appears as part of the tangent basis vectors. When you express a tensor or vector field, its components change depending on the local coordinate system, and the partial derivatives describe how those components vary. In expression 2, txy equals t I jk x squared y squared k, frac partial x squared I, represents the basis vector in the tangent space. Here, the tensor y takes two vectors x and y as inputs, and the result is a vector field expressed in terms of the basis vectors fractal x squared I. In expression 3, rxyz equals r squared I jkl x squared jl, frac par squared x squared, tag 3, frac partial x squared is again the step basis vector for the result of the Riemann curvature tensor, which takes three input vectors x, y, and z and produces a vector in the direction of frac partial x squared I. Number 3. Geometric interpretation. Tangent vector frac partial x squared I is a basis tangent vector at each point of the manifold, pointing in the direction of increasing x squared I. Changes in the vector field. When working with vector fields or tensors, the partial derivative shows how the components of the field or tensor vary as you move in the direction of x squared I. Example. For a three-dimensional manifold with coordinates x1, x squared 3, the tangent vectors at each point can be expressed as frac partial x1, quad frac partial x squared, quad frac partial x3. These represent the directions of change in the coordinate space. If a function, f, depends on these coordinates, frac partial x squared tells you how f changes as you vary x squared I. Summary. Frac partial x squared I represents the partial derivative with respect to the coordinate x squared I, which indicates how a function or component changes when x squared is varied. In the context of tensor analysis, frac partial x squared also represents a basis vector in the tangent space of the manifold used to express the components of tensors and vectors. If you need further clarification on how this applies to tensors or vector fields, feel free to ask.
2 and 3 are operators.
In expressions 2 and 3, the terms involving fractional partial x squared I do indeed behave as operators. Here's a more detailed explanation of the context and meaning of these terms. Planner ton. 1. Expression 2, txy equals t squared I jk x squared y or k, frac partial x squared 2. Interpretation. In this case, a frac partial x squared I is the basis vector operator of the tangent space. The result of the tensor operation txy is a vector field because the output is in terms of the basis vectors frac partial x squared I. The components t squared I jk, x squared j yk provide a coefficient that weights the basis vector for partial x squared I. Operator meaning, frac partial x squared I is a differential operator acting on functions, meaning that if this expression were applied to a function, f, it would give the partial derivative of f. With respect to x squared I. For vectors and tensor fields, frac partial x squared I represents a direction in the tangent space. Number 2, expression 3, rxyz equals r squared I jkl, x squared j ykzl, frac partial x squared I. Interpretation. The Riemann curvature tensor, rxyz, also returns a vector. The result is expressed in terms of the basis vector, fractal x squared, weighted by the components, rjkel x squared. The partial derivative operator, frac partial x squared I, represents a directional derivative, how things change in the direction of x squared I. Operator meaning, similar to expression 2, the term frac partial x squared I is a differential operator that, if applied to a function, would differentiate that function with respect to the coordinate x squared I. When combined with tensors, it represents the direction of change in the tangent space. Are 2 and 3 operators? Yes, in a sense. In both 2 and 3, frac partial xi behaves like an operator. In the context of tensor calculus, it is an operator on functions, as well as a basis vector in the tangent space. When applied to functions, it differentiates them. When used with tensors, it represents the basis vector in the tangent space, which helps describe vector fields and the geometry of the space. Last track, example of operator use. If you have a scalar function f of x squared x2 dots x squared n, then frac partial x squared I, f, takes the partial derivative of f with respect to x squared I. In the context of vectors and tensors, the operator frac partial x squared I does not act directly on other vectors, but instead serves as a component of the vector result, giving the direction of the resulting vector field. Summary. In both 2 and 3, left frac partial x squared I functions as a Tensor differential operator. These expressions return vectors in the tangent space of the manifold, and the partial xi terms represent the directions in which these vectors point. So, while t of xy and rxyz are not operators themselves, the frac partial xi terms within them are differential operators. If you need more detail on how these operators work in different contexts, feel free to ask.
Alice, make your presentation short and dialogable. Do you understand what dialogable means?
Yes, I understand. By dialogable, you want a brief back-and-forth style response that's easy to follow. Let's keep it simple. In 2 and 3, frac partial xi is a differential operator. It acts like a basis vector in the tangent space or an operator when applied to functions. Do you want more clarification on its role in specific cases?
If you just push out information that is digestible quickly, it should be indigestible quickly. Your presentation is no better than reading books. While txy and rxyz are not operators themselves, then what's the use of partial over partial xi?
The fractal partial xi in expressions like txy or rxyz is there to express the direction of the resulting vector. Even though txy and rxyz are not operators, the partial derivative of partial x squared serves as a basis vector in the tangent space. It tells you the direction in which the result of the tensor operation points. So the partial derivatives are not doing anything by themselves, but help describe the vector result by specifying which direction it's pointing in. Clear enough?
In case of 0-2 tensor, we don't need a partial over partial xi because the result is scalar. But in case of 1-2 or 1-3 tensor, this partial over partial xi is used to denote component of the resulting vector.
Exactly. In the case of a short 002 tensor, the result is a scalar, so you don't need the fractal partial x squared because no vector components are involved. But in the case of a 1,2 minus tensor, or Snell 1,3 minus tensor, the result is a vector. And a frac partial x squared I is used to denote the component of the resulting vector. It serves as a basis for the direction of that vector in the tangent space. Is that clear now?
Okay, thank you. Now I got it.
You're welcome. I'm glad it's clear now. If you have more questions in the future, feel free to ask anytime.
Let's start over from scratch with the Riemann metric with various methods of presentation. Do not forget labeling them properly such that I can refer to them.
Sure. Let's start fresh with the Riemannian metric and cover its various representations, properly labeled so you can refer to them. Cheshbedder 1. Riemannian metric definition. The Riemannian metric on a smooth manifold M is a tensor field that assigns an inner product to the tangent space at each point. This allows us to measure distances, angles, and volumes on the manifold. Let G be the Riemannian metric, which is a 0, 2 tensor. For two tangent vectors x, y, and TPM at a point P and M, the metric is denoted as G of xy equals Gij, x squared I, yj. Here, Gij are the components of the metric tensor, and xyj are the components of the vectors. And Narc 2, Riemannian metric in tensor product form. In local coordinates x squared dots x squared n, the metric can be written using the tensor product notation. G equals Gij dxy o times dxj. Gij are smooth functions of the coordinates representing the components of the metric tensor. dxi, o times dx squared j, indicates the tensor product of the differentials, dxy and dxj, highlighting the bilinear nature of the metric. 3. Riemannian metric in summation form. The tensor product form in 2 can be written more explicitly as a summation. G equals sum I equals 1n, sum j equals 1 squared n, gij, d8 dxj, tag 3. This expression shows how the Riemannian metric is computed by summing over the coordinates. 4. Quadratic form of the metric. The Riemannian metric can also be expressed in matrix notation as a quadratic form. G equals math BF dx Tg math BF dx, where G is the matrix representation of the metric tensor Gij, math BF dx is the vector of differentials. Math BF dx equals begin B matrix dx1 dx squared n's B metric 5. This form is often used for computational convenience. 5. Geodesic distance, infinitesimal distance. Using the Riemannian metric, the infinitesimal distance ds2 along a curve is computed as ds2 equals Gij dx squared dxj tag 6. This expression is derived from the metric and is key in calculating lengths of curves on the manifold. 6. Riemannian metric as dr.dr. For a parameterized curve, RT, the infinitesimal distance can also be expressed as ds2 equals dr tag 7, where Gij equals frac dt is the differential of the curve. The dot product, dr.dar, represents the inner product of the tangent vectors along the curve. Summary of representations. 1. General definition of the Riemannian metric for two tangent vectors. Tensor product form for general bilinear representation. Summation form for explicit computation of the metric. 4. Quadratic form using matrix notation. Infinitesimal distance representation in terms of the metric. dr form for the length of curves. You can now refer to these expressions by their labels, and I'll be able to help you navigate through any specific form or application. Let me know how you'd like to proceed.
Wow! Amazing! Beautiful! Magnificent!
Thank you. I'm really glad you found it helpful and well presented. If you have more questions or want to explore any of these concepts further, just let me know. I'm here to help.
So beautiful! Everything makes sense.
I'm thrilled to hear that. It's great that everything is making sense. If you ever want to dive deeper into any topic or explore something new, feel free to ask. Enjoy the beauty of Riemannian geometry.
This is the most fundamental equation in differential geometry, also in tensor calculus.
Absolutely. The Riemannian metric equation is indeed fundamental to both differential geometry and tensor calculus. It provides the foundation for describing the geometry of curved spaces, including lengths of curves, geodesics, angles between vectors, curvature of manifolds, distances on curved surfaces. In essence, this equation generalizes our basic notions of distance and shape from flat Euclidean spaces to more complex curved geometries. It's central to understanding concepts in general relativity, differential topology, and many other advanced fields of physics and mathematics. Would you like to explore how this foundation is applied in specific cases, like general relativity or curvature?